am Eleni Zavrakli, and I'm a fourth-year PhD student based at University at Hamilton Institute. I am part of iForm, Advanced Manufacturing Research Center, and the focus of my project is machine learning and feedback control for additive manufacturing. And in the context of my project, when we talk about machine learning, we're specifically talking about reinforcement learning and deep reinforcement learning. The motivation behind my project is the fact that real-time quality control is one of the main challenges occurring in additive manufacturing today, with a lot of decisions on safety and product quality needing to be made, usually under uncertain or incomplete information. So we are aiming to monitor the manufacturing process through sensors and use the data to make intelligent decisions and implement corrective actions. Now, the main families of methods that we're working with are feedback control algorithms and reinforcement learning algorithms. In the feedback control framework, a controller is designed offline using knowledge from some underlying model of the system, and then it's brought online and uses the output of the system to adjust the input in order to achieve the desired behavior. While on the other hand, reinforcement learning assumes an artificial agent that learns from interacting with the environments, making decisions only based on its past experience and gaining rewards or getting burdened by costs based on how good the decisions were. An important extension to reinforcement learning is deep reinforcement learning, where the decision-making agent is replaced by a deep neural network, and that allows us to scale previously intractable problems, such as problems with high-dimensional state or action spaces. Now, to test, compare, and eventually combine all of these methods, we have been using a temperature model, a model of the temperatures within an extruder head of a 3D printer, specifically a fused deposition model in 3D printer. And we're using this model, it is in state space form, which makes the model-based algorithms easy to design. And we also use it to simulate and generate data for our data-driven algorithms. The state of the system is the temperatures within the extruder head, and the input to the system is the input of the heaters within the extruder head, as well as the motor of the extruder. What's important to note here is that sometimes we have the entire state available to us, but more often we only have some measurements of the state available. Now, as expected, our model-based algorithms are doing really well at achieving our optimization goal, which we have chosen to be bringing and maintaining all the temperatures at 180 degrees. And the model-based algorithms perform really well, even in the case where there's sufficient noise present, and that is thanks to the Kalman filter. An important result of ours is that we managed to achieve comparable and almost identical performance with our data-driven algorithm. We were specifically using Q-learning, but in the case where the full state is available to us. We're currently working on achieving same results where in the case where we only have some measurements of the state available, but more widely known as the output feedback case. Now, the next step in our research is to apply all these problems, all of these methods to real life problems. Namely, we have acquired a Prusa MK3S, which we'll be using as our application. We will be using all the data that the printer acquires itself, as well as temperature measurements from an infrared temperature sensor that will be pointing at the surface. And additionally, we will be attaching 2 digital microscopes, also pointing at the surface and taking pictures of the quality of the surface. And those pictures will be used to formulate the reward for a reinforcement learning algorithm. So to sum everything up, we believe that deep reinforcement learning will allow us to save a lot of time and materials and give us a better understanding of potential defects in the build, which will eventually lead to a wider adoption of additive manufacturing methods in industry due to the increase in accuracy and repeatability of the build. We also believe that benefiting both from an underlying model of the system and obtained data will result in a higher efficiency and accuracy for the 3D printing processes. Thank you.